Okay, so welcome back, everyone. Today we're going to continue our discussion of using methods like k-nearest neighbors to do what we'd call local methods in learning. And we'll explain kind of what the intent is behind that, and what we mean by this idea of locality. And then in class today, we'll talk about an algorithm for trying to achieve this notion of finding nearest neighbors efficiently. This particular algorithm we'll discuss is locality sensitive hashing. So in this video, I'm not going to talk about LSH at all. I'm going to be talking about some recap of this idea of k-nearest neighbors, as well as thinking about how we could use nearest neighbors approaches and other approaches that use local information when trying to work in the context specifically of regression. So as a reminder, last time we started talking about classification and using something like k-nearest neighbors to achieve that. In particular, one of the things we thought about in the context of document retrieval were these notions of precision and recall. They're metrics you could use to identify how effective your model is, and again, they're different metrics that mean different things. So precision is out of all of the things that you predicted positive, what ratio of them are actually positive? So of the things you predicted positive, what fraction of them were correct? And in this case, if we predicted 6 things as positive and 4 of them actually were positive, then our precision is 2. Recall, on the other hand, is all about, did you find the things that actually were positive? So out of all of the examples that actually were positive, which examples did you flag as positive? So in this example in our data set, there were 6 rows that had a label of positive, and only 4 of them did we correctly predict positive. So in this case, our recall, which is just the number of things we flagged as positive that are positive, in case, in other words, the true positives, divided by the true positives plus the false negatives. False negatives being the things that actually were positive, but we labeled as. And that ratio tells us how much we are able to find the things that are positive. Talked about how there's generally this trade-off between precision and recall, particularly in the context of recommender. Now, the big context that we're focusing on today is in this case study of thinking about document retrieval, trying to find the most similar documents. And you'll find one of the things that's a bit weird about this week is we're going to be talking about document retrieval kind of intermittently. The reason being a lot of the ideas and techniques and the reason why we're talking about document retrieval apply to things like classification well. And so when we're talking about things like embeddings for documents, that's all stuff you could also use in a classification. These are all tools, and then how you use that tool depends on context. So we'll come back to this document retrieval over and over again, but today we're really going to be focusing on kind of a lot of the stuff we built from here, thinking about how to use local methods. And when we're thinking about document retrieval, we're really thinking about how do I say, given a text document, find the most similar ones? And that brings up a lot of questions. How do you measure similarity? How do you actually go find the ones that are most similar? And what does the accuracy of such a system sound like? And our big idea from last class was defining an embedding and a similarity metric, and then using some type of nearest neighbor approach to find which document was the closest. So as a reminder, in terms of embeddings, we talked about things like bag of words or TF-IDF. There are ways of taking abstract documents like a text document and turning them into features of numbers that we are used to working with. We talked about a similarity metric, a way of measuring how similar or how far apart 2 documents are. We talked about lots of examples, but 2 common examples are Euclidean distance, cosine distance. Just numeric functions that take 2 embedded documents, either bag of words or TF-IDF, and output how similar they are, or in this case, how distant. You can imagine similarity to being the inverse. And then we used an algorithm, like some nearest neighbor algorithm, to find, if we have a document or a book we're looking for, go find all the things that are the most similar. Where most similar is the closest in this embedded space. So if you had some document here, this is our query article shown in gray, then maybe we'd return the blue article because it's the one that's closest in this space. And all of these representation decisions are really important and will affect what do you recommend as the most similar document? That was a kind of our context for this week of document retrieval. Now, we're going to shift gears a little bit and talk a little bit more about regression. And in this video, like in this particular video, we won't have too much tie into document retrieval. But in class, when we're talking about locality-sensitive hashing, that's going to be an efficient way of trying to find this nearest neighbor document. But we're going to show that there's other applications of neighbor approach methods. So as a reminder, way back in week 1, we were talking about regression with housing prices. And what we were doing there is we were assuming that there was some model that determined how the world worked, that there was some true function that approximately told us the price of a house for. And the modeling choice was, do we assume it's linear? Do we assume it's a square or a cubic function? Or many other choices. All we had to do in that context was choose the right polynomial degree to match this true unknown function. Now, what we're really doing here is we're trying to model the problem globally. What I mean by that is we assume that there's one function that applies to every point in this space. That there is one global rule that says, oh, yi is approximately some true function f of xi, but we know that rule was a bit noisy, so we allowed some noise. So we were assuming some kind of global model, that there is one function that for every point determines what its output should be. Now, we talked about that context quite a lot. But one problem with that context is if you don't know that assumption, there isn't just one. Maybe the function's really complex, or you don't really even understand where you could start modeling a function. And so if we want to ignore some notion of global structure and just assume maybe things behave more locally, then we might try to do local methods. And so what I mean by that is instead of trying to find this one true globally defined function, what if we just try to infer the value of a point using examples nearby? So here's a big idea. Use one nearest neighbor to predict the price of a house. Instead of trying to learn some global function that we could then use for prediction, if you want to predict the price of a house, just go find the most similar house and use that one's price. This is actually not the craziest idea in the world. This is often what a lot of realtors do. If they want to figure out the price of your house, they might just say, well, this house is very, very similar. We'll just use this as a prediction. They might have a more complicated model in their head. Oh, well, this is LA, and so maybe this price increases. But a baseline, this is actually not a terrible model. Just find the most similar house and then use that price. Now, what this looks like in the context of regression is if you imagine our example of square footage house and trying to predict price, we might have some example points. And then if we're ever interested in finding the price of, say, a house here, we just find the house with the closest square footage and then predict its price. Now, what I've drawn here in green is essentially the predictor that for any square footage x, find the nearest example in our training set, in this case one, and then predict its price. And so what you end up having is these kind of areas of just constant predicted prices. But there are kind of switch points where when you get halfway between 2 points, you go from the prediction from one to the other. And so here is just me drawing out what's the prediction for every possible square footage. And the way I do this is just find the nearest example in our training set and predict its price. And so all of these kind of flat regions are all of the points that have so this whole region are all of the points where this one blue point is. And once we cross over and another point is its nearest neighbor, then we jump to another prediction. So this might seem kind of reasonable to do in this context of, this might be a really good baseline in terms of what realtors do, but you might kind of see a little bit of a problem here. A small example that the prices fluctuate quite a bit. It jumps up and down. There's this kind of discontinuity, and we'll talk about how that might. But this also works when you have more data. So on this right side, I have a picture of a plot with more data. You can imagine that here, our nearest neighbors for points like here would be this first point. And maybe it would go just a little bit past until it reaches halfway. And it would jump up to this point. And you can imagine it will end up just kind of always predicting the output of the closest point, always switching off halfway in between. A little hard to draw. So on and so on. And that gets pretty close if you imagine in the grand scheme of things, even if there is some kind of global function predicting everything, this one nearest neighbor approach gets pretty darn close, assuming the noise is small and that we have enough data. That it's kind of fitting the general trend, but not by looking globally, only by looking at points nearby, making the assumption that points that are similar should have similar housing prices. So, in a sense, it's just another modeling choice, but it's one that's not trying to model the global structure of the problem. It's not trying to find a degree 3 polynomial that works for every point. It's really just looking at nearby points, making decisions. So here's the algorithm for one nearest neighbor regression. You are given some input query, xq. That's the point that we're interested in searching, making a prediction for. And we have a training set of n examples. What we'll do is we'll just find the one nearest neighbor of x in our training set, and then output its label, where one nearest neighbor is the algorithm I described last time to find the single nearest neighbor of a point. So searching over all the points and finding the. Now, what this ends up doing, if you imagine this in higher dimensions, where you have maybe two features, it's learning functions that we might call locally constant, meaning each region where the nearest neighbors are the same, all of the outputs will be the same output. It doesn't change until we move to a new nearest neighbor. And so you could imagine and assume if we had two features, say x1, x2, you could imagine trying to form these regions of here are all the points that are closest to this one. So for example, all of the inside this cell are the closest to this one. And so within any individual cell here, the prediction will be the same. The prediction will be whatever the label is of that training point. We sometimes call this kind of visualization a Voronoi tessellation. It's a way of trying to visualize kind of how nearest neighbors are working and kind of what it's trying to do. It's saying any point that's closest to this point is going to get the same label. Now, in general, you're not going to actually compute this Voronoi tessellation. It's just a visualization tool to show what's happening. But you'll end up seeing that if you make predictions with this, well, wherever a point lands in, say, point land here, the predicted label would be whatever this one says, because this is its nearest neighbor. And this is a way of visualizing the space of all nearest neighbors, or all the outcomes of. Now, the reason I like to use this kind of visualization of a Voronoi tessellation is it helps us understand a key distinction that I've kind of left out, which is how do you measure the distance between two houses? This actually comes back to a question we discussed on Monday, is how do you define a similarity metric? That yes, you probably wanted to say something like, well, maybe if we're just using square footage as our feature, maybe it's just the distance or the difference between square footage. But choosing how similar or how different things are is a modeling choice. It's a choice of how you represent your data. And so different representations of what's similar and what's not might lead to completely different types of predictors when using one nearest neighbor regression. So, like last time, if we change what it means to be closest, it's going to change what we think our model might be. So last time we talked about two really common ways of defining distance, one being Euclidean distance and one being Manhattan distance. So again, if we have 2 points, the Euclidean distance between these 2 points is the square root of x1, I should do x1, 1 minus x2, 1 squared plus x1, 2 minus x. That's just the square root of the sum of the differences. That's our Euclidean distance that we talked about last time. And we also talked about the Manhattan distance, which is the sum of the absolute values. So this is going to be the x1, 1, absolute value, plus absolute value of x1 minus x. And this is our Manhattan distance. There are two different ways of measuring distance. How you use this definition of distance will change what does it mean to be a nearest neighbor. So here I have examples of what does this Voronoi tessellation look like when you use Euclidean distance versus Manhattan distance. The idea is the same. You form these cells where all of the points in one cell are the nearest neighbor to one of our training points. But the geometry of those cells is going to look very different because which function we use changes the distance metric. And so here with Euclidean distance, you'll see these kind of like nice kind of patterns that aren't circles, but they're kind of like these dividing planes between 2 points, finding these equal. But in the Manhattan distance world, things look very different because it's all about not these kind of distances along diagonals, but distances along the axes. And now if you look at this, say, this point, both of these things, which points are its nearest neighbors looks very, very different. Now, which choice is the right choice? There's generally not one right answer. This is all about kind of how you think the world should work in terms of representation. But I just wanted to mention, and I wanted to highlight the fact that these distance metrics affect how you define these local methods or what the output of these local methods. But again, you don't actually usually compute these Voronoi tessellations in practice. They're really just a visualization tool to see what's going on. So let's talk a little bit more about one nearest neighbor regression. This thing works quite well in practice, or in some cases, when you have lots of data with little noise. But there are some pretty key weaknesses with one nearest neighbor regression. In particular, if your data is sparse, meaning it's very spread out, then it's not going to interpolate very well. We'll see an example of that. And it's very possible for one nearest neighbors to overfit quite a bit. So what I mean by that is if you have a lot of data with very low noise, then it's very, very good, this one nearest neighbor model. It actually finds lots of, or the general trend is. However, if you have parts where you're missing data, so for example, if you have a data point here and a data point here and nothing in between, well, then we get these bigger jumps because there's less data to interpolate between. It's not doing anything fancy. Smooth function. It just has what's the nearest neighbor, and at some point, the midpoint, it switches over to the next point. So you can get these really jagged things. It's not very good at interpolating between large gaps. And also, in particular, if you have too few data or more noise, then it could wildly overfit. That it would look very, very like an over. So how might you go about actually trying to prevent that? How might you prevent that overfitting? That's what we're going to talk about in the rest. What I want to mention real quick is that you could totally do all of this visualization stuff we're going to talk about today with classification. We talked a lot about that on Monday. But today we're going to be focusing on regression in context. So how might you prevent overfitting? Well, the downfall of one nearest neighbor comes from it relying too much on a single data point neighbor, which makes it susceptible to data that's very noisy. So I think a fairly intuitive idea is if you want a more reliable estimate, look at more than one house. So instead of using one nearest neighbors, make it k nearest neighbors. And then say predict the average of those k nearest neighbors. I think this idea of looking at more houses to make your result less variable is something that should be a little bit intuitive from what we discussed before. The details of how you make that prediction that you want to find k nearest neighbors be a little bit trickier, but that's the key idea. Just use a larger k. And if you use a larger k, well, then the function you'll learn is going to look very different. Instead of bouncing up and down wildly because it's always switching whatever is the nearest neighbor, you'll end up learning a lot smoother of a function in some. Because if you're looking at the average of 30 neighbors, if you're moving kind of from point to point along this line, the overall majority of this group isn't changing too much. You have 30 nearest neighbors, And if you just move over a little bit, maybe to this point, well then you'll maybe kick out one nearest neighbor and include one more. But you're still taking the average of 30 things. How do I compute this green line? Well, for every value of x, I find the 30 closest points and then take the average. And this averaging over a larger range makes this function learned less jagged. It makes it kind of smoother and something, bouncing up and down quite a lot. You can make this function a little less crazy by using larger or larger k. Now, things to note about this is not a perfect approach. There are still discontinuities that when you kick a neighbor out and include another, that's going to still change the output in a discrete way. And so you'll still see these steps, like you can see in this green function, that still steps up and down, but the steps are less pronounced because we're averaging over more. And even kind of worse of a problem is that the boundaries, the thing at the edges, look kind of wrong, right? When we're talking about all of these points here kind of get the same label because the 30 nearest neighbors are kind of all the same. And it's not really being able to learn that the true function that generated this data kind of down there because we don't have data showing a further downward trend on the left. So here are some issues with k-nearest neighbors for regression. That while k-nearest neighbors can solve some of the issues one nearest neighbor has, it brings more to the table. In particular, you have to choose the right value of k. If k is too large, the model is too simple. If it's too small, it's too discontinuities might matter in a lot of applications, but having that kind of stepping function might be really bad. The error might be better, but would you really believe that you'd see this drastic change in price by increasing the square footage of one? That might not lead to the most interpretable model in all contexts. And then also this problem with the boundaries is still there, and so we probably need. So one idea to fix this is this idea of weighted k-nearest neighbors. Instead of treating all k-neighbors equally, weight them to maybe try to smooth out this process a bit. So the idea is, instead of just taking the average of the k-nearest neighbors, for each nearest neighbor, have some weight. And here I'm being, it's a little complicated notation, but I'm saying here is this weight CQ, nearest neighbor J, is the weight, why isn't that right? Oh, I didn't. The weight between point XQ and its nearest neighbor, X nearest neighbor. So I'm going to have some kind of weight between these two examples. So if I have, say, some data points, maybe my XQ here, then I have maybe X0, X1. I'm kind of making weights based off these distances between them. The intuition being that because a point is much closer, maybe I want to put more weight on it than at some point further away. Okay. So how do you choose these weights? So that's going to be a modeling choice that we're going to do. Ideally, if the distance between the 2 points is large, we want the weight to be small. And alternatively, if we want the weight to be large, if the distance between them is small. So weighted k-nearest neighbors would somehow be using some type of weighting scheme to do k-nearest neighbors, take the average, but instead of a straight average, it's a weighted average. How do we learn these weights? That's something we'll talk about. So here's the idea. You could imagine there's lots of ways of trying to turn a distance into a weight. And in fact, there are many, many ways. Generally, this approach that we use to turn distances into a weighting scheme is what we'll call a kernel. A kernel is a function that turns distances into weights in a way such that small distances get large weight and large distances get small weight. So what we'll do is we'll define a function called a kernel that takes the distance and outputs a weight. Now, there are many, many such functions you could define. Here is a graph that shows 1, 2, 3, 4, 5, 6, 7 of them. 7 different ways, and this is not all of them, to take a distance and output a weight. On the x-axis, we're going to have, of these graphs, is the distance. What distance are you outputting or inputting? And on the y-axis is the weight assigned. The intuition is as you get closer and closer to the center, distance being 0, the weight increases. But the exact details of how you decrease the weight as the distance increases, each one of these kernels has a different idea of how it should go about. Now, one important point before I explain what these kernels are trying to do, almost all of our kernels are going to be parameterized with this thing called lambda. We call lambda the bandwidth. And this is a hyperparameter that tells you how much or how wide should this kernel be. How much distance should be allowed. If you use a larger bandwidth, you're going to be allowing looking at points further and further away. If you use a smaller bandwidth, you really want the points to be close. A kernel is just a mathematical function that takes a distance and outputs a weight. One very common kernel is what we call the uniform kernel. And this is, in some sense, the simplest kernel you could think of. It's a function that assigns equal weight to any point within the bandwidth. So here on the x-axis, we have between negative lambda and lambda. The uniform kernel, shown in orange here, just assigns the same weight all of the things inside of it. You can imagine that with the uniform kernel, you're really just doing unweighted k nearest. Just unweighted k nearest neighbor. I'll mention just because it comes up that oftentimes this uniform kernel is also called a boxcar kernel because it looks like a train car. See that thrown around a lot, so I want. There are lots of other kernels. I'm not going to talk about most of them. The two that I find very useful, one is the Epinechnikov kernel, this one, and then also the Gaussian. Most kernels have this notion of peak in the center and then decaying as you go further away, but which mathematical function you use just changes based off this. The Epinechnikov kernel is this blue function. Importantly, outside of the bandwidth, the kernel value is 0. And that's true for a lot of the kernels we use. A lot of the kernels say if you're outside the bandwidth, I'm going to assign 0 weight. And another very popular one is the Gaussian kernel. And the Gaussian kernel is an exception to this rule, where it does not assign 0 weight to things outside the bandwidth. It's just a normal distribution. It uses the same formula as we used before, for the most part, where it's centered at distance 0 and then spreads out from there. And the bandwidth determines how wide you want it. But if you choose larger and larger lambda, it's going to be more and more spread out. If you choose smaller and smaller lambda, it's going to be more spiked towards the center. But importantly, it doesn't ever assign 0 weight. It's going to assign some weight every point because this function, the normal distribution, gives non-zero value to every point that's defined for the entire domain. Now, this seems really complex, but I want to highlight the fundamental idea is very, very simple. Make a function that takes distance and assigns large value to small distances and small values to large distances. The way you actually write that function has many, many different ways. There's lots of functions that have output that's large when input small and vice versa. And here we're just showing you some of them. We call these functions kernels. Uniform doesn't have any shape to it outside of this like uniform value. The Epinechnikov kind of is this bowl looking thing that has 0 value outside the bandwidth. And then Gaussian is kind of this. All of these kernels are parameterized by bandwidth, lambda. And that tells you how wide you want these things. We'll talk about how you choose. But assuming you've stuck to one kernel, then you could do something with that. So instead of talking about k nearest neighbors, I want to talk about this other regression approach called kernel regression. So instead of just restricting yourself to the k nearest neighbors, just use the kernel to weight all of the points. So when you get rid of this notion of the k nearest neighbors, and you just weight all of the points by the kernel, we get kernel regression. In this case, it's the same thing as the slide I showed you before. It's just but we're looping, this kind of sum loop goes for all of the training points, and we weight it based on the weight between the query point Q and the point I in our training set. And how are those weights defined? It's just whatever the kernel says for it. I think this will help a lot more with a visual example. So here, I'm going to be using the Epinechnikov kernel, using a bandwidth of 0.2. Now, what that means is that when we're kind of doing this loop over the entire data set, we're going to find the weight for our query point, this point in red in the middle, and every point in our training set. Now, for example, here, we're going to look at that point, take its value, and multiply it by its weight. Its weight is going to be whatever the output of that Epinechnikov kernel. I haven't shown you the formula for it. The formula is kind of fun, but I don't care that you know. It's just a function that kind of has this kind of upside down bowl looking shape. We're going to take that value, weight it by whatever the kernel says based on the distance between these 2 points, and then add that to our weighted average. And we'll do that for all of the points in the data set. Now, for many of these points in the data set, like this, the value for it, Ci, is going to be 0, because the Epinechnikov kernel has value 0 if you're out more than lambda away. We're still technically adding it in, but weighting it by 0. So it doesn't do anything in reality. What this yellow kind of region is showing kind of along the x-axis. The height is showing you the value of the Epinechnikov kernel. So the taller this yellow region is, the more weight you're assigning to points in that. And so we're taking this weighted average over all of the data points, but only the ones highlighted in red here actually have non-zero weight. And then we output them. Note, importantly, from all of this, what you end up learning, the function, if you just use this Epinechnikov kernel to make predictions for every possible x point, this function you end up learning a lot smoother. And that's because you don't have this kind of discrete, like in or out and equal weighting throughout. Is as points get further and further away from the query point, they contribute less. And so you get a much, much smoother function rather than just k nearest neighbors. It turns out you'll learn for most of the kernels, you'll see similar behavior. The one exception is the boxcar kernel, because that's very similar to k nearest neighbors in some sense. But for most of these ones that kind of go down towards 0, and then once you hit your bandwidth, have 0 kind of weight to them, you'll see a much smoother curve because it's using, in some sense, all of the data points. It turns out in practice, which kernel you use has a much smaller impact than choosing the bandwidth correctly. If you make your bandwidth too small, you're not going to be taking this kind of weighted average over lots of points. So here is using the Epinechnikov kernel again. On the left, I use lambda as 0.04. On the right, I use lambda as 0.4. And you can see here with the small lambda, because I'm kind of kicking points out that are even a moderate distance away, you get a much bouncier function up. Whereas if you use a larger lambda, you get a much, much smoother and flatter function. The worst case where if you make the bandwidth infinity, it's just the average of all of the points. So choosing the bandwidth generally it has a much effect. Now, if you use something like the boxcar kernel, you'll still get something in between. You'll get a different function learned, but it's pretty similar in some sense to what you might expect using the Epinechnikov kernel. Maybe a bit different with those up and down spikes or steps, but in general, your bandwidth is really the thing you have to do correctly, not so much. So how do you choose what right settings you are? Well, you use cross-validation or validation settings. You can use it to choose kernel, you can use it to bandwidth, and also if you're using weighted k nearest neighbors rather than just kernel regression, you want to find the k closest and then you can also choose the right value of k there. So nothing surprising there, just cross. that's all I have for today. We'll pick up in class where we will kind of recap some of this stuff, do some examples trying to compare them, and then talk about an algorithm to efficiently find k-nearest neighbors when you want to